My name is Peter Shah. I'm from the NetApp Advanced Technology Group, and I'm going to be presenting Lamassu, which is a research prototype we've been working on for a little while. It's targeted at providing storage-efficient encryption services at the host end, which is to say somewhere near an application. I'll start off with an overview of what we were trying to do, and then I'll move on to talk a little bit about how the encryption techniques we took and where we were heading with them, and how our security model is put together, at least at a high level. And then I'll talk about the systems problems we addressed and what our solution is focused on, followed by a taste of the experimental results to say, does it work and what are the effects of it, followed by my conclusions. So when we started this thing, we were looking at how do we make encryption services sit near the application, so perhaps on the same system, or the operating system, or the file system layer. And we were looking at that in the context of being able to treat our storage as untrusted. So the example I've given here, because it's a nice intuitive one, is public clouds. But you could also imagine just wanting to tighten up your security model and say, my shared storage is cool, but I'm going to make it outside my core security boundary. What we really want to do is draw the tightest possible boundary around my application, or in this case, I've shown a set of applications. And they're all streaming a series of some kind of chunks of data into shared storage. And what I did not comment on, but was in the previous slides, they're being deduplicated in that storage cloud at the bottom. But I said I wanted to apply encryption. I'm trying to draw this trust box around my application. And of course, that's great, and it produces security, and it makes my data harder to steal. But it means that my data now looks like random noise, at least by standard encryption techniques, and so my deduplication goes away. And I don't like that because I like not storing lots of extra data. So we set the next goal. We'd like to do this preserving storage deduplication at the storage backend without making it appear in my security regime. I don't want to give it the encryption keys, and I really just assumed it not even know I was doing my encryption. So to do that, we used an existing technique called Convergent Encryption and sort of use that as the basis for building our system. And I'll talk a little bit about what that means and how it works in the security section. And finally, we didn't really want to build this into a single application, and we already are not working with the storage system. So we started to structure things so this is completely transparent. So I've shown Lamassu as a mystery box at the edge of the security zone, but importantly, it's basically just encryption services as a layer and does not have any hooks into the application or into that mystery storage zone at the bottom. And to the extent possible, we'd like to keep the whole thing self-contained so you can be just that layer you slide in wherever you like. I put an asterisk on there, as we'll see later on. It is not 100% self-contained. There is a little external piece that I'll comment on. But for the most part, we've got everything running just through that little box, sitting inside that data stream. As I mentioned, I'll talk about the security and convergent encryption. And just to provide a basic definition that we're working with, we're treating convergent encryption as any encryption technique that preserves the property that, given the same clear text, you will always deterministically encrypt it into the same ciphertext. And the nice property for that, and I should mention, we're doing fixed block deduplication with this system. It means that if I give you a block today and you encrypt it, I will get a ciphertext. And if I give you that same block tomorrow, or a different client gives you that same block tomorrow, that will go to the same ciphertext. So that means if I store both of them at the storage backend, good news, they'll be deduplicated. The most common build for this, the thing you'll see the most in literature, is what's called message lock convergent encryption, or MLE. And what's going on with that is, instead of having a secret key, as you might have in conventional encryption, they'll take the data chunk, and I've called it a block here because, as I said, we're doing fixed block encryption, and they'll take a cryptographic hash of that block. And rather than using a secret key, they'll pipe that hash right back into the encryption mechanism. I'm using AES here because that's what we use as a convenient standard. But you could imagine plugging in a different encryption system of your choice. And since that is now functioning as your key, you get a ciphertext. And the property that is nice about this is anybody who has the clear text can generate the key and therefore generate the ciphertext. And it's a deterministic encryption, so the ciphertext should always be the same given the same block. When you decrypt, you simply reverse all the arrows and you feed that block key right back in and you get your data block right out. But there's a question here, which is, when I do this, where did that block key come from? I mentioned earlier that I have to have the clear text to generate it. And if I don't already, and presumably if I'm decrypting, I don't already have the clear text. So the question becomes, what do I do with that thing? I clearly have to save it somewhere. And so that's really the focus of our work, is how do I want to manage these keys? For fixed block encryption, you can imagine, for even a modest sized data set, I'll have thousands, tens of thousands of these things if they're on a per block basis. And so that becomes a significant thing to take care of and store somewhere. And this is where that asterisk comes in. You also need some way to, when you store them, we're trying to be transparent and self-contained, and so we're therefore also trying to store this. So we'd think it'd be cool to store the stuff kind of in the same storage area. We don't want to have to build a side metadata service or a side key service to store all these tens of thousands or hundreds of thousands of keys. So what we're going to do is encrypt them using standard encryption. The keys are certainly much smaller than the data itself. And we'll store them on that same storage device in the background. And then the question becomes, how do we structure that? We've treated this key management problem as a metadata issue. I have some quantity of many little tiny pieces of information associated with my file, and without them, my file is essentially useless. It's encrypted, and I need to have them in order to get my data back. So what I've shown here is a very simplified picture of a very small file and a few little keys stuck next to it. This is not shown to scale. So our solution is to embed those keys inside the file's data stream. The nice property for that is if everything is mushed together into one large file, that means the storage system, which as I say is not participating in my security plan, my security strategy, all it will see is a file which is slightly bigger than the original file. It doesn't know what the original file looked like, so it sees a stream of bytes. And that means if it manages things, if it replicates things, if an administrator or someone comes along and moves the file somewhere, the keys go with it automatically. And when I read the file back, the keys come back with it. Now, the problem with just scattering them everywhere you want, of course, is that we're doing deduplication on a fixed block basis. And if I start changing the contents of blocks by interspersing keys with them, I'm polluting my data with these weird random keys that are not going to deduplicate nicely. They're encrypted, they're already cryptographic hashes. They're basically pseudo-random numbers as far as deduplication engines are concerned. The other thing, of course, is it can mess up my block alignment for deduplication, which can also change what is and is not deduplicated. So our strategy is to segregate the keys out from the data. I'm showing you here a picture. Again, there's a very small file. So all the keys are mushed to the front of the file, and then there's some wasted space to preserve block alignment. But in this situation, you can at least see those 4 blocks should be more or less the same block alignment and should be deduplicable, and the keys are in an identifiable location. Now, of course, we want to be able to extend the file beyond some fixed size, and we don't want to have to rewrite the entire file every time we add a key beyond some point. So the way we structure things in Lamassu is to view a file as basically an array of segments. We break it up into a series of chunks. So picture this as a file of some arbitrary size broken up. Inside each of those segments, I build a little structure similar to what I showed you earlier. At the front of the segment is a little metadata region, which is full of keys. And following that is a whole series of data blocks, which are all convergently encrypted. Now, for security purposes, that front metadata region is AES encrypted with that shared secret key. It is not convergently encrypted, and it wouldn't really deduplicate against anything anyway. But all the data blocks are convergently encrypted with keys stored in the metadata region. And as far as the application is concerned, it sees its file read through Lamassu, just like it's written through Lamassu, as if it started at that logical offset 0 as all of its data. And if I were showing more than one segment in the expanded picture, you'd see the logical offset continuing to slip away from the physical offset, whereas the storage system is just seeing an array of bytes starting with the physical offset and going to some length. And, excuse me, inside that metadata region, what you see is there's a little bit of metadata there that is described in our paper, which is used administratively to help our system run smoothly, but almost all of it is taken up by basically an array of keys. And those keys, the keys in one region map to the data blocks that follow it. Of course, by embedding the keys in the file and having a key in a metadata region as well as data, I've introduced a potential consistency problem in that your file is utterly useless if they become unsynchronized. or at least your segment at the very minimum. So I will preface this by saying Lamassu is assuming a relatively reliable storage system at the back end. We are assuming that the file system will handle getting a block to disk or failing to get a block to disk. So I'm not presenting here a mechanism for handling a partial block write. But in the event that there's a failure and a block does not make it to disk for whatever reason, because of network failure or our software failing, we do have a mechanism for that. If I start with a state like this, which is, again, a version of a Lamassu file, in this case, I've inserted a key and a block, which go together inside this picture. And I want to update it. I'll generate a new version of the block, n prime. And that block comes with a key, a conversion hash key, also n prime. In order to do an update, what I want to do is first, I want to update the metadata region for the segment that owns that block. And when I do the update, I'm going to write it such that both versions of the key, the old one and the new one, are present. And the reason for that is that if I were to fail in this state, it means that when I come back and look at my file again, I know that I have the key that reads that block. I may not immediately know which one of those two it is, but I know one of them does, and I will be able to verify between the two of them which one I want later on. If I don't fail, then I go on and update the data block, and I get into a better consistent state where my new key and my new block go together. And eventually, in future updates, Lamassu will clean up the keys, and the exact details of that mechanism are outlined in our paper. So now I'm going to talk about results, but before that, I'll describe the structure of our prototype now that I have the basis for how the encryption scheme is basically laid out and the primitives we're using. Because we wanted to experiment with this in a fairly portable way, we wanted to build a nice self-contained module. We thought it'd be very convenient to build our system as a file system encryption layer in Fuse. That lets us prototype it very quickly, and as I wanted to have it be transparent to applications, this means that any application we picked on Linux could talk to us through the VFS layer. I'm showing the same cartoonish series of data blocks coming in, getting encrypted and stored and deduplicated here, as I showed at the beginning of the presentation. And the main takeaway here is Lamassu is sitting on its own and just sort of inserting itself in the data path in our prototype, as was in the description. I've shown here an NFS connection to the shared storage because that's a major way we were testing it. But since we're just going through VFS and standard file system interfaces, you could imagine this could be an object interface out to a cloud. It could be a local disk. It could be a tape library if you insist. Something that would work. You can plug basically anything in there, but the deduplication should work, assuming those services are available. The other piece I've shown in here that was not described earlier is a key manager. And this is really where that asterisk and the self-containment comes in. We're not using a key manager, as I've already described, to manage all of our individual block keys, but that one shared secret we're using to secure the metadata regions, we are actually putting into a key manager. And the reason for that is we wanted to have a secure way of distributing a shared secret among multiple applications. If I have 1,000 clients that all want to share the same key and get the same deduplication services, they'll all need to share at least that one key amongst themselves. And that's where the key manager comes in to distribute the one master key, basically. For testing and comparison purposes, we picked a series of file systems to compare against. The first one is something we've labeled plainfs, which is a Fuse-based file system, so we could get an apples-to-apples comparison with the Fuse overhead essentially factored out as a control. But this one's just a pass-through file system. It really doesn't do anything. You give it a write, it issues the same write back to Linux. The next one we picked is another file system called ENCFS, which is also Fuse-based, and this one's an encrypting file system. It uses the same AES mechanism we're using, but it's not doing anything convergent. And both of these are open source file systems that we picked up externally, and they're cited in our paper if you want to figure out where the code for those is. And finally, in our test, what you'll see is Lamassu FS, the third bar in all of our graphs, which is our prototype, which is again Fuse-based. It's again using AES. But of course, we're using our convergent encryption, and we were curious how that would work out for deduplication, performance, et cetera. So the first and most critical question is, does this thing work at all? So I've got here a graph showing deduplication results from our experiments with all three of these file systems. Along the x-axis, what you're seeing is how much redundant data was in the test data set we've pumped in through each test. And along the y-axis, you're saying is how big was the data set after it was deduplicated. And what you'll see is fairly intuitively that the plainfs column, which is the first one, in each case, every redundant block was located and deduplicated, and you get a linear relationship between redundancy and final file size, data set size. And with the encrypting file system, because it's using standard AES, what you'll see is no deduplication happens, and the data set is always 100% size, no matter what the internal structure of it was. And then, of course, the one we're trying to push here is Lamassu FS, which you'll see is very close to the plain FS line, but it's not actually quite the same. I put a line here to help you see where the difference is. Lamassu FS has a very small overhead in there, and in all 5 cases, you'll see there's a little bit of extra space taken up, and that's coming from our metadata. There's a little bit of metadata, there's a little bit of file padding if you're not on an even segment boundary, and those result in somewhat less than 1%, depending on some tunables, of the raw data set size as an overhead. But assuming you wanted the encryption in the first place, it's certainly a much bigger savings than you get with the basic encryption. The next 2 things I'm going to talk about are about throughput, and basically there's a question of measuring what was our I/O overhead, what was our computational overhead for doing these convergent things. The first one I'm showing you is exactly the setup I had in that slide, architectural slide earlier, writing through all 3 file systems through NFS to do deduplicating store. And along the x-axis, I've got a series of different I/O patterns we've put through it just to see if they behave differently. And along the y-axis, I've got a relative scale for amount of data throughput. And to no great surprise, in all cases, the non-encrypting plain file system is the fastest. But what you'll see in most cases, ENCFS doing plain AES and Lamassu are pretty close together. In the 2 right cases, you'll see Lamassu has a much more noticeable hit. And the chief reason for that is that metadata updating process, which is creating some write amplification in the I/O. And of course, in the NFS workload you're seeing here, the write latency is meaningful over NFS, and so that's creating some performance change. And there's some more details in our paper about various trade-offs we experimented with in that process. Having observed that and observed the write amplification effect, we were curious to see how the hash computation and convergent processing affected our performance without worrying as much about the write latencies as a separate component of our performance. So this chart is showing you performance done against a RAM disk, so we could eliminate that expensive network hop and get much more of a picture of what the computational overheads were of our system versus the others. And what you'll see here first is that on the y-axis, I've changed things up on you and put a log scale on here instead of the linear scale in the previous graphs. Otherwise, the x-axis is the same. And the reason for the log scale is that against the RAM disk without NFS, plain FS, the do-nothing file system, takes off. That bar on the sequential read test case represents something like 2.5 times the performance of the 2 encrypting file systems. But leaving that particular element aside, what you'll see is ENCFS and Lamassu FS are now much closer together. That hash overhead is measurable, it's a real overhead, but it's not gigantic. So we think that's actually pretty promising. So as conclusions, I said we wanted to do encryption and strong security, and we thought convergent encryption was a good approach for it, and certainly it preserves our deduplication. I thought about putting up a slide of some random line noise garbage to prove that we encrypted things, but I figured you'll take my word for it. We're preserving storage-based deduplication. Our overhead relative to what you're going to save in a deduplication-friendly workload is pretty small. Probably if 1%, or it's actually about 0.8% in our current case, if that much space overhead is a huge problem for you, you probably weren't getting a big win from dedupe anyway, and you might want to use a different system. We didn't have to modify either of our 2 endpoints, which was a big win for us. And finally, we think that building our prototype in Fuse as this self-contained user mode process makes it very good, convenient to port around, which we think is cool. So hopefully it can show up in some other system in the future. So with that, I will take questions.
Questions?
Yeah.
This is pretty neat stuff, but I do have a question.
Mm-hmm.
One of the things that people pick on about convergent encryption is its susceptibility to a confirmation attack. That is to say that even if I can't read the contents, if I have something, I can check to see whether it's identical to what you stored.
Correct.
Because I can hash it and encrypt it myself.
Right.
Do you think there's a way that you can handle that so that you'll be more resistant to that?
Yes. So actually, there's actually a discussion of this in our paper. So the question is basically, convergent encryption is depending on the entropy in your data to keep yourself secure, because if it's easy to guess what your data is, an attacker can guess that instead of your key. And that's a known weakness. So the answer is, for us, we picked a simple solution, which is to introduce actually a second secret key. So we're actually modifying the hash with an extra secret element to prevent that. So essentially, everyone who's in the same deduplication trust zone has an extra shared secret to modify the key. There has been other work published by some other authors, they're cited in our paper, to do more sophisticated things, including involving a key manager in a more complex key generation. But yes, we're aware of the problem, it's a real problem, but there are solutions for it. We picked a simple one.
Thank you.
Thank you.
I have a question. So have you considered like timing channel attacks? Because the way you implement that is you're using fuse, and I sort of can test if your system has a block by just storing someone, observe the time it takes to store.
So the assumption would be if you store it through our system or you store it onto the same storage?
Through your system, and if you already have that block, then the storing time will be differently shorter. And I sort of can guess, sort of brute force and guess if I could.
So the answer is you probably cannot, because if you don't share this, so going to the previous question, if you don't have that secret, your data actually won't be deduplicated against my data. So your guess will always, your guess won't change depending on what I stored.
Thanks.
Thank you.
So let's thank the speaker again.